Today I will be talking about A-STEP, which, as you mentioned, is a technology demonstrator payload. It's actually a ride-share payload, so we're not talking about a full sounding rocket here. So it's about a 3-kilogram box, and we plan to fly in Subtech 10 hopefully next year. Despite it being a small ride-share technology demonstrator, I'd be negligent if I didn't quickly mention the science. We'd like to explore the medium energy gamma ray sky in more detail with some future large gamma ray observatory. There's a lot of very interesting science that can be done in this regime, much of which is multi-messenger and time domain astronomy, which is a big focus of the 2020 Astrodecadal Survey. However, one of the reasons we want to fly this medium energy gamma ray observatory is that you can see on the figure on the right here, we have this bit of an MeV coverage gap from hundreds of keV through a couple hundred MeV. This is a plot of continuum versus energy. So as you go further down in the plot, your sensitivity, it shows better sensitivity. And the hard X-ray new star does a great job. And the GeV energies, Fermi-Lat dominates and does a really great job, but we have this lack of coverage in the MeV. This isn't because we don't want to do it. There's a lot of very interesting science that can be done. Here's a more explicit case. We're interested in studying AGN hadronic acceleration as a big contributor to the cosmic environment of ultra-high energy cosmic rays and other types of accelerated hadrons. What could occur in these AGN or proton accelerations? You have these protons that are accelerated. You have these cascade of interactions that result in photons and neutrinos that can be measured here on Earth. In 2017, IceCube made these first measurements of neutrinos they believe came from a blazar source, or Texas 0506. If you can couple these with gamma ray observations, you can learn a lot more about these accelerators. Fermi-Lat did see some flaring of this source, at least in one case. However, there are other cases where these neutrinos were observed where there was no Fermi detection. So a dedicated medium energy gamma ray telescope could tell you a lot more about these accelerators. Again, this hasn't been done not because it's not interesting, it's just because it's very hard. In these energies, you have to contend with both Compton scattering as well as pair production in terms of ways your photons will interact with your detectors. On the right here is just a plot of what a medium energy gamma ray telescope could look like. It's usually a multi-instrument system. You have a tracker telescope comprised of many, many layers of usually lower Z tracking detectors, where you're basically attempting to prompt the photon to interact with your detectors, either scatter it or split that photon into an electron-positron pair. You then continue to measure those photons or particles as they travel through your system to a high Z, high stopping power calorimeter below, where you try to collect the rest of the energy of those interactions. Usually this is wrapped by an anti-coincidence shield that blocks your other charged particles, but that's not included in this image. Pair production's a little bit more straightforward. You have a positron and electron, you track them, you can reconstruct where the original photon came from and localize the source. With Compton imaging, it's a bit more tricky. You measure both the location and energy deposition of at least 2 of these scattering or absorption locations. And with this knowledge, you can reconstruct an annulus on the sky from where this photon could have arrived from. When you stack a bunch of these photon annuluses, you can slowly reconstruct your source. And this is very tricky to do. You need many, many layers of these detectors. You need to have very good energy knowledge of these interactions. Any additional passive material you introduce in your system or any gaps in your detector planes will introduce loss of efficiency in your system. So you want to minimize those as much as you can. And so you really want a technology that is both low power, because you need many, many detectors, high tileability, as well as good energy resolution. We're working on a detector technology called AstroPix. AstroPix is a high voltage monolithic active pixel sensor. I won't be talking too much about the detector itself here. Regina Caputo will be actually giving a presentation this afternoon more about the detector technology itself. I do want to just briefly mention that this is, explain what a monolithic active pixel sensor is for those who don't know. Monolithic just means that your silicon is both your detecting medium as well as your readout integrated circuit. It's all in the chip. So there's no hybridization or attachment of other type of detector medium. An active pixel sensor, each pixel is a parallel independent readout chain that amplifies the incoming charge and then digitizes it right on chip. The digital data is passed to the edge of the chip, where it's just bucket brigaded down or using an SPI interface from chip to chip. so it doesn't require much of a front-end system. On the left here is just a list of Astropix requirements, and right now for this sounding rocket technology demonstrator, we plan to fly a 2x2 centimeter Astropix version 3 chip. So ASTEP, or the Astropix Sounding Rocket Technology Demonstration Payload, is really just to advance the TRL of these detectors. This will be the first flight of Astropix detectors in a space-like environment. Really, for this payload, we primarily just want it to work and to telemetry down real data as it flies, but we have set a bit of an objective for ourselves, which is to measure the cosmic ray rates we observe on orbit or in space, and reconstruct those particle tracks as they hopefully pass through multiple layers of our detectors. We will be flying ideally on a Subtech 10 launch next year with a nominal flight duration of over 10 minutes and some apogee above 200 kilometers. The ASTEP sounding rocket, the instrument is pretty straightforward. It's 3 layers of Astropix chips. We're calling these quad chips. Basically, you take these from the wafer and you dice them in 2x2 active pixel sensor arrays. So you really have 4x4 centimeter detectors. You then put these on these instrument boards and stack the instrument boards together to get your instrument. For ASTEP, we plan to fly 3 of these boards. You can see the quad chips picture there on the left with wire bonds, handling power, as well as some clocking. And then those 2 chips on the bottom actually have this flex print printed circuit board that covers them that allows you to do this wire bonding without having to do it directly to the PCB. Of note, we're only talking on each of these layers to 1 of the 4 chips. The data is bucket brigaded or passed, both the data and the commanding is passed from chip to chip, so you only need to talk to the closest chip in the array, which is great if you're trying to tile many detectors. On the right here is just a bit of a systems architecture. You have these detector layers. We'll have 1 FPGA that will interface with all 3 layers, and that FPGA will be supported by a single board computer, which will be flying a BeagleBone Black, as well as some telemetry and high voltage biasing from a separate board. So just a bit more about the payload design itself. On the left is our mechanical model, just exploded so you can see all the different parts. We'll have a power distribution unit that'll take in power from the sounding rocket at 28 volts on 1 tray and slightly isolated from everything else for thermal reasons. Then we'll have another layer which includes our BeagleBone flight computer, this high voltage biasing board, as well as the FPGA board. The next layer up, on the sidewall, we'll have mounted our Astropix carrier board stack. The reason we mount it on the sidewall is that this box actually sits on a tray within the sounding rocket itself, and we are in this evacuated section of the sounding rocket, which will open up to space during flight. So by mounting on the sidewall, when this shutter opens, we can actually see right out into space and have less aluminum in front of us for better counting. On the right, you can just see images of our hardware. We have actually most of the hardware in hand already. In the top right, you have the power distribution unit on one part of the mechanical tray, and then on the other one, you have the FPGA, the computer, and the high voltage bias. And this isn't a very large box. It's about 2.5 to 3 kilograms, maybe a bit less, and it's about half a foot by half a foot. This is some early testing we've been doing. We haven't calibrated all the chips yet, but we're currently in the process of collecting our flight hardware and doing some of these calibrations. This is a very interesting heat map because there's actually a lot going on. Usually heat maps can be kind of boring. So on the left here is just an image of this Astropix quad chip board where you have chips labeled from 0 through 3, and that corresponds with each of your heat maps on the right. There's some features you can see in these heat maps. First of all, anything that's white is a pixel that's turned off. The first 3 columns of each Astropix version 3 chip is turned off. These were test rows that included a different type of amplifying circuit that turned out to be noisy, and we don't want to end up flying, so we've just disabled those rows. You also notice that there's a bit of a different coloring in terms of the top chips 2 and 3, where you can kind of see the count rate's a bit lower, and that's just because of the copper in the flex print bus bar covering up some of that, those counts at lower americium energies. And lastly, you see this interesting trace of turned off pixels that passes through your top 2 chips. And this is due to we're calling it an interrupt signal from your flex print bus, which basically is a fast trigger. It lets the front end system know when data is ready to read off from the chips. And it turns out that when it enables, it's actually been triggering our pixels. So we had to disable those pixels right below that trace. So we'll have to improve that for the next design. Multi-layer testing is underway in the lab. We started this relatively recently. Right now, we're just using charge injecting and some beta sources to attempt to do some coincident measurements between multiple layers. So basically, you have a cosmic ray or your beta source or an injector that's triggering in multiple pixels on multiple layers. And you can create some 3D space of your 4 chips per layer and your 3 layers and attempt to demonstrate that you're getting similar timestamps. We've also done some simulations in terms of what we expect to see while we're on orbit. These were done by Dr. Albert Roy from Hiroshima University. He assumed some background at 300 kilometers and 30-degree inclination to look at what kind of charge distribution of energy deposited we're going to get in our 3 detector layers. This was at a depletion for our detectors that is approximately 70 to 100 micrometers. And we predict a on-orbit 3-layer interaction rate of a little bit less than a hertz, but we'll have to target this in a bit more due to the fact that I don't think this includes all the thresholds that we are accounting for. Lastly, just a brief coverage of the schedule. Right now, we have most of our hardware already in hand. We have a 3D printed mechanical assembly, as well as the first revision of our mechanical assembly design. We'll be expecting delivery of the full mechanical payload a bit later this month or maybe next month. We have our first flight boards in hand. On the bottom left, you actually see we've encapsulated the wire bonds going to each of these detectors. This is primarily for high voltage rather than for any vibrational concerns. We've already done vibration testing of these systems, and they proved to hold up very well. We plan to, by the end of the year, finalize some of our detector software, with flight software being finalized in early 2026. System integration payload testing will conclude in mid to early 2026, with hopefully a flight in August or later in the year. So thank you.